Right, this is Physics 1101, Chapter 10 on fluids. This will be Chapter 10A on fluids. So I'll talk about today is liquids in general, because this is basically, I mean, fluids can include gases, but we're only going to be dealing with, for the most part, liquids here until we get to the second part of the chapter, which deal with Bernoulli's principle, which deals with a gas as a fluid. So you can have fluid gases, fluid liquids. As far as that's concerned, we're going to start with fluids per se, and introduce the concept of pressure, which we've already talked a little bit about before, which is force over area, right? This is in newtons, and this is in meters squared. And we've already talked about density, which is mass over volume, right? So, and we've talked, a little bit about, well, we haven't got too much in that, but this is the concept of density, like how much does two objects compare, right? You have an aluminum cylinder and a brass cylinder. Which one is densest? Which one is heaviest? Well, the aluminum was bigger, but this one is denser, so it has a greater mass to it. We'll talk about that. So we're going to get into the concept of pressure, which is force over area. And what this means is if I have a certain amount of weight, all right, say this thing, say, weighs 1 kilogram, all right, has a mass of 1 kilogram, which using force is mg, which is weight, then this will be 1 times 10 meters per second squared. So this mass has a weight of roughly 10 newtons, all right? Now we talk about pressure is, if I have pressure, I have a weight, but how is that distributed? If I hold it in my hand like this, it's spread out over quite a bit. If I put it this way, I mean, I'm still holding some of my weight, but it's more focused on one part. And this creates what we call pressure, so it's force divided by a certain amount of area. So if I have this spread out over, say this is, 1 centimeter, a couple centimeters on each side, right? One object, then area, say the area is roughly A is roughly 4 centimeters squared, meaning 2 by 2 centimeters. Now convert this back to meters squared. Remember, 100 centimeters is 1 meter, but 10,000 centimeters squared is 1 meter squared. So you move it over 4 decimal places, so 4 centimeters, you start 1, 2, 3, 4, right? That is equal to 0.0004 meters squared. I believe it's correct, 4 10,000s, yep. So then the pressure of this thing, which is force over area, the pressure will be given as 10 newtons over 4 times 10 to the minus fourth, which is roughly 2.5 times 10 to the fourth newtons per meter squared, or this unit of Newton per meter squared is also known as the Pascal, PA for short. So that's the unit we have for pressure. Force over area, it's going to be in meters squared, newtons per meter squared. So this would be the pressure for that. Now, say I have it on a point like this, so that it's a much smaller surface. And if I actually make it really sharp, so that I have it like just the tip, if I could do that, not gonna, if I've had just the tip, so like almost a needle type shape, then the area, instead of being 2 by 2 centimeters, the area would be approximately 1 millimeter by 1 millimeter, so 1 millimeter squared. We're also getting back into conversions again. 1,000 millimeters is 1 meter, but 1 million millimeters squared is 1 meter squared. So it's moving it over 6 places. So if I have 1 millimeter squared, that's equal to 1 times 10 to the minus 6th meters squared. So the pressure, if I had just a point, like if I could actually twist this so it's just standing on a point, and this weighed 1 kilogram, the pressure then would be 10 newtons over 10 to the minus 6th meters squared, which would be 10 million, 10 to the 7th pascals, or which is this, Pascal. That's a very high pressure, all right? That's a very high pressure as far as that's concerned. So we're introducing this concept of pressure, and it's force divided by a certain area, all right? So that's the first thing here. Now, when we get into this concept, I mean, there's pictures in the back of the book, where they talk about, all right, which of these containers has the pressure greatest at the bottom. And I have a similar thing here. I have 2 containers. One has water level here, the other has water level here. Now you can see this one has a smaller area than this. So you might ask, which one has the greater pressure at the bottom? And the concept might be that you might think that, well, this is more mass, this is a lot bigger, so the pressure is going to be bigger at the bottom. Well, that couldn't be more wrong. The one that is deep pressure only goes as the depth for liquids. It's the depth that makes a difference. It's the depth for gases too. It's how much weight is above it, not above a certain area. So the pressure here is actually much greater than it is here. I mean, it's the same kind of thing if you ever put out a concrete sidewalk, right? And it's a big area, but it's only this deep. You don't need much in the way of wood to keep it in place. However, if you have a big wall, you need to make sure it's really reinforced at the bottom, because if it's deep, even if it's thin, the pressure at the bottom is going to be enormous compared to this. So the pressure only depends on the depth. Actually, it does not depend on the volume as far as how big this is at all. So this one has a higher pressure. So we get into this concept. We've got the concept of pressure, which is force of area, and we'll talk a little bit more about density, which is mass over volume. Okay. So again, here's our conversions: meters squared to centimeters squared, and meters squared to millimeters squared, which will be useful for some of the problems. All right. So let's move on here, and then So the concept of density. Density, I'm just going to use mass over volume. And there's a table that shows, so it's either in kilograms per meter cubed or grams per centimeter cubed. And what we're going to have here is we have a certain table. There's a table that shows different liquids or such. And part of it is, the standard we'll have is water, H2O, as a standard density of 1,000 kilograms per 1 cubic meter. So that's the density is 1,000 kilograms per cubic meter. Now that's also equal to 1 gram per cubic centimeter. So we'll get into the concept when we talk about specific. So this is the density of H2O. But if we talk about specific density, all right, this will be density rho compared to density of water. Okay? So if something has a specific density of 2, that means its density is 2 grams per cubic centimeter, or 2,000 kilograms per cubic centimeter. Or if it has a specific gravity of 0.5, it means it's 0.5 or 500, depending whether you use kilograms per meter cube or grams per centimeter cube. If we're dealing with smaller sizes, like these objects here, we generally deal with grams per cubic centimeter. And if we're dealing with big objects, then we generally use that. All right, so that's the density of water. You can have some other comparisons. Aluminum is 2,700 kilograms per cubic meter. Brass, not bromine, but brass is approximately 9,000 kilograms per meter cubed. We also compare other things. Let's see, where is ice? We talk about liquids. We talk about ice. We talk about solids. That's 917. That's why it's about 10% less dense. So it's about 10% less dense, which is why ice floats on water. Right? It's one of the unique properties, as we'll see, about ice and water, is the fact that as you freeze water and look at the density, right? So if I plot density versus temperature, all right? Then as we cool something, the density is going to go down, go higher and higher as it gets cooler and cooler, but then it reaches a certain point at 4 degrees Celsius, and then it starts to cool again. So this is one reason ice, it floats. This is also one reason why we have life as it is, because of the unique property that water, when it freezes, becomes less dense. If it was the other way around, if it became denser, then it would sink, lakes would freeze from the bottom up and would never melt because there's nothing to melt the water at the bottom. So it's kind of a unique property as far as that's concerned. All right. So we have that. We also have air. which has a density, which is mostly nitrogen, and has a density of a roughly 1.29 times 10 to the minus. That's 1.29 kilograms per meter cubed. So it's about 1,000th the density. All right? So when we talk about pressure, though, of air, or pressure at all, pressure is, again, this is an area. Pressure is force over area. And how we define this then is then, if we go back to English units, what we have is, if we have 1 inch squared, that weighs roughly 14.7 pounds. This is the pressure of air at sea level, roughly 14.7 pounds per inch squared. It's also, so it's the weight of all the air above us for every inch squared. Every inch square of atmosphere weighs about 14.7 pounds. In other units, we have, it is defined as the one atmosphere, this unit, and it's also equal to 1.01 times 10 to the 5th newtons per meter squared, or pascals. So roughly 100,000 pascals is 1 atmosphere pressure. So these are all equivalent. We call it 1 atmosphere's pressure at sea level. So sea level. And it's either 14.7 pounds per square inch or 1,000, about 100,000, 101,000 pascals per pascals, or 101,000 newtons per meter squared. Right, so that's the density of there. And so that's for air, and we'll be talking about that later. As we pressure in atmosphere, pressure as we go higher up in altitude, pressure will drop because there's less atmosphere above you, and there's less weight there. So that's a bit of that now. This more deals with meteorology, but these are the basic units for atmospheric pressure. All right, but I'll move on to water, because we're going to be using that extensively. And so the density of water, right, is 1,000 kilograms per meter cubed. And again, H2O. And if you look at the pressure, pressure goes as force over area, which for water, if you have a certain volume, is the density of water times the area. So you have a certain volume, which would be the cross-sectional area, A, times the height, the depth of the water, and so times the height times G over the cross-sectional area. So A cancels out, So the pressure of a fluid is given by rho times the depth of the fluid. So in this case, it might from this point to this point, and times G. Now, what we see here then, if we put in roughly density of water, so this is 1,000 times G is 9.8, or let's lose roughly 10 meters per second squared. This will be 100,000, 10,000 times the height, or depth in this case. All right, so the depth would be how far we're going down into the water. All right, at the bottom, it would be this depth. And what we'll see, our atmospheric pressure, 1 atmosphere is roughly 100,000 pascals. So this will be in units of pascals, 10,000 times H. So if we are at a depth of 1 meter, so if H is 1 meter, then P will be 10,000 times 1, or 10,000 pascals. If H is 10 meters, or roughly 33 feet, then P will be equal to 10,000 times 10, or 100,000 pascals, or roughly 1 atmosphere. What this means is every 10 meters, you go down depth. So this is surface level. We just talked about the pressure. We'll get down to 10 meters. Here's the pressure. P is 0, just the water. P here will be 1 atmosphere. Go down 20 meters. P will be 2 atmospheres, and so on. So relative to the surface, as far as just the water, every 10 meters gives you 1 atmosphere pressure. And so what we have here then is going to be then, the pressure plus, if we add the atmosphere pressure, P of atmosphere, right, then the pressure will be this plus 1, this plus 2, this plus 3. Right, so this is important in diving, because then at surface you've got 15 atmosphere, 1 atmosphere pressure. You go down 10 meters, you've basically pressured, you have twice the pressure on you as far as you get. 3 times, you go down 20, it's 3 times as much. So this is an important concept of diving as far as that is concerned, right? So, the higher the pressure difference, the greater it's going to be. An example here is a water tower, which is a nice picture here. And what a water tower does is not so much to have a big sign for the city, but what it does is they pump the water way up, a few meters up, all right? And maybe in this case 30 meters. So what we have there then is the pressure. This is 30 meters. Then the pressure of the water on the bottom, this will be P will be 30 times 10,000, which will be 300,000, or roughly 3 atmospheres. if you want it in terms of pounds per square inch, 1 atmosphere is roughly 15 pounds per square inch. So 3 atmospheres would be roughly 45 pounds per square inch, which is quite a bit. So this gives you a nice pressure, consistent pressure. They pump the water up, let it store, and it gives a consistent pressure to all the water coming out without having to have a pump it out. So this is the concept of pressure as far as that's concerned. So I mean the difference here compared to here. It's the same thing with hydroelectric dams, right? You have a dam where the water is up at this level. You have your turbines down at the bottom. The pressure depends on the depth. So this is a very strong pressure down here, which is why you want dams to have very tall, because that's the greater the pressure, the more force it's going to put on the turbines to drive the water. So that's a little bit of the introductions there as far as that's concerned. All right, so in chapter 10b, I'll summarize this a bit more, get into Archimedes' principle and such. So that's it for today.